Another quick example problem. Now, this one's kind of interesting in that not particularly difficult, but conceptually is interesting. We have a long, thin solenoid, and it has a number of turns per unit length of 400 per meter, so 400 turns per meter, and it has a cross-sectional area of 10 square meters, that's A1. And the current, I1, that's in this long solenoid that I've got drawn here, is increased from 0 to 50 amps in 2 seconds. And then wrapped around that, or around that, we have a plain loop of wire that has M2, 10 turns, that's this outer one here. But it has a larger cross-sectional area. It's 10 times the area, and so it's a loop that encloses 10 or 100 square centimeters. And this outer one, this outer coil of N turns has some resistance, 0.05 ohms. And it's placed around it. So basically we have this ring, and then we stuck this solenoid, this long and thin solenoid in it. And we need to find E2 and I2. That's the EMF that is induced in the this outer ring, and the current that's induced in that outer ring. If I view this edge on, then I have a very thin solenoid here, and I'm going to assume the current is going in this direction. It's going to be increasing. We're increasing from 0 to 50, but it'll be going in this direction. And if you remember for the solenoid, at least for a very long solenoid, the magnetic field is coming out at you, and that's these points here. But it's only on the interior of the tube of the solenoid. There's no magnetic field generated on the outside. Okay? This other ring, when I view it edge on, is out here. Okay? And as these as the magnetic field gets stronger and stronger due to the current increasing in the long thin solenoid, the magnetic field will have more and more field lines coming out of the page at me. And so the induced current in this outer ring will be such to oppose the change of flux through it, which is only in this small portion, but it'll create a current that'll flow in this direction, so by the right-hand rule, it'll tend to cancel out as you curl those in through this area here. It'll tend to cancel out the flux lines there produced by the long thin solenoid. Well, we know what the magnetic field is due to the long thin solenoid. It's 0 outside, and it's I call it mu naught N1 I1, where 1 is the first one. And the EMF that's generated in 2, the 2 is this large ring around. That's the number of turns times the time rate of change of the total flux through the area enclosed by the loop, which is this big area. But and that, in general, is a magnetic field strength times the area. But mostly, there's no magnetic field cutting it, because the only magnetic field that's cutting through that the area of the second coil is inside the solenoid. So you don't use A2 here because mostly it's 0. That doesn't give any contribution. The only part that will give you flux through this area of the second coil is the magnetic, where the magnetic field is non-zero, which is B1, this magnetic field up here, times A1, which is the area of the thin solenoid. Well, again, I can then plug this into here. The area of A1 doesn't change any. That's the area of the thin solenoid. N2 is the number of turns, which was 10 turns. And the only thing that that changes is this magnetic field inside. It changes because the current is going higher. Then I get this. Actually, I can bring A1 outside. There's A1. But the magnetic field B1 is mu naught little n1 times I1. Well, mu naught's a constant, little n1's a constant, area A1 is a constant. I can pull all of those outside to get this. And then it's just the time rate of change of the current in that the long, thin solenoid. And I know how that's changing. It's going from 0 to 50. So again, I don't worry too much about the direction of it, or the direction necessarily. But to a good approximation, this di dt can be the change in the current I1 over the change in time. And now I've got everything. N2, that was just 10 terms. Mu naught, well, that's a fundamental constant, 4 pi times 10 to the minus 7th Tesla meter per amp. N1 was 400 per meter. Area 1, that's the area of the small coil, which was 10, or the small solenoid, that was 10 square centimeters. But again, we need to make sure everything is in MKS units, so I need to convert centimeters to meters. And I know in 1 meter there's 100 centimeters, but that'll only get rid of one of those, so make sure you square that to get 1 square centimeter on top, and 10 to the 4 square centimeters on top, square meter on top, and 10 to the 4 square centimeters on bottom. And then the current goes from 0 to 50, so the change is 50 amps, and it does that in 2 seconds. And if you multiply all of that up, you get, I got this number here. I kept the minus sign in this. It's not real relevant in this particular problem. One gets a 10 Tesla meter squared. That should be a meter squared. This meter will cancel this one, but I've got and this centimeter will cancel this one. The meter squared here, so that should be meter squared. And a Tesla meter squared per second is a volt. Right? Do that. And I converted it to microvolts, but that's sort of irrelevant on this. We could have left it in terms of pure volts. What about the negative sign? What's that telling us? Well, it's telling us that if the current in this one is going around this way and increasing, so it's getting stronger and stronger in this counterclockwise fashion, that the induced current in this outer one is going to be in the opposite direction. So as you can figure out from the right-hand rule and Lenz's law. But that's the interpretation of the minus sign. Usually I would just probably take the magnitude of it and just figure out the direction like I did first of all. The EMF, we know the resistance, so we can get the current. And it's just like any other EMF at this time, even though it's induced by Faraday's law. It's an induced current. And when I did it, I got the minus 2.52 milliamps when I plug in that voltage over the resistance of the wire in that larger circular coil around it.